Have you ever wondered how we build a map of a city that has never been seen before? Imagine walking into a dense, unknown metropolis for the first time. You don't have a name for the streets, you don't know where the vital businesses are located, and you certainly don't know how the residents move from one neighborhood to another. All you have is a chaotic screen full of thousands of raw GPS coordinates, latitude and longitude points flickering in the dark. In the world of high-resolution mass spectrometry, those GPS coordinates are your M/Z features. By themselves, they are just noise, isolated, lonely points of data in a massive, unorganized ocean. But your goal as a high-level researcher isn't simply to collect coordinates. Your goal is to see the streets and the traffic flow. You want to see the biological pathways that define life, characterize disease, and measure environmental impact. Welcome to Module 10-2, the Omics Pipeline. The pro move, the true difference between a technician and a scientist, is understanding the pipeline architecture. Today we build the bridge from raw data to biological truth. Let's learn how to see the forest through the trees. Before we get into the software, we must address the philosophy of data stewardship. Why not just report the top 10 tallest peaks and call it a day? Because in systems biology, the truth is hidden in the biosignature, the complex, interconnected pattern of multiple metabolites that define a state of health or a specific toxicological response. If you are on the discovery path, your primary challenge is methodological alignment. You have to ensure that every step of your data processing preserves the biological signal, while ruthlessly filtering out the chemical noise. In this session, we are moving from coordinates to context. By following this pipeline, you provide a validated, logical rationale for your biological conclusions. This is what we call analytical certainty. It is the ability to prove that your data isn't just a collection of numbers, but a map of reality. Let's look at the 4 major steps that will turn your raw harvest into a systemic masterpiece. To successfully navigate the omics pipeline, we utilize a 4-step framework designed to distill complexity into clarity. We begin with Step 1, the raw harvest or spectral processing. This is where we clean the fog from our map through feature extraction and noise filtering. Next, we arrive at Step 2, the identification gate. This is the critical stage where we assign names to our coordinates using the Szymanski scale of confidence. Once we know who our molecular residents are, we move to Step 3, the deep insight. This is pathway analysis, where we use sophisticated statistics to distinguish between who is simply present and who is actually working. Finally, we reach Step 4, mapping the system. This is the visualization stage where we see the interconnected web of life. Each of these steps is a filter, turning 5,000 raw peaks into a clear, 1-page biological summary. The journey begins with spectral processing. Think of this as the raw harvest. We start with a messy file straight from the instrument, and our first job is feature extraction and peak picking. Your mass spectrometer sees everything: chemical noise, solvent contaminants, and actual biological molecules. We must use algorithms for baseline correction and noise filtering to clear the fog. But in a modern omics study, we usually have dozens of samples, which introduces a major logistical problem: retention time drift. If the same molecule elutes at 10.1 minutes in sample A and 10.2 minutes in sample B, the software might treat them as 2 different molecules. This is why spectral alignment and feature normalization are the pillars of trust in our pipeline. We align the internal clocks of every single run to create the Feature Quantification Matrix, or FQM. This is the organized census of your city, ready for the next stage of investigation. Now that we have our list of organized features, we hit the identification gate. You have a precise mass of 192.0757. But what is it? To answer this, we must use the Szymanski scale to communicate our certainty. In a high-performance lab, we always aim for level 1, a confirmed structure. This means you've matched the exact mass, the retention time, and the MS/MS fragments against a real reference standard. However, in discovery workflows, you will often live in level 2, a probable structure, or level 3, a tentative candidate. This is where we leverage massive spectral databases like the Human Metabolome Database, METLIN, or Mass Bank. Think of this as a database search for your city's residents. You might not have their DNA profile yet, but you have their photo and their address. Your job is to move as many features as possible from unknown to identified. This is the heart of the module. Once we have identified our metabolites, we must ask, what does this mean for the organism? We answer this through metabolite set enrichment analysis, or MSEA. We have 2 primary methods, ORA and QEA. Think of overrepresentation analysis, or ORA, like a roll call in a classroom. You ask, are more molecules from this pathway present in my sick group than I would expect by random chance? It tells you who showed up. Quantitative enrichment analysis, or QEA, is much more sophisticated. It asks who is working the hardest by looking at actual concentrations. If 10 metabolites in a pathway are all increasing by 500%, that pathway is clearly active, even if the total count of molecules hasn't changed. Using tools like Metabolomics, we turn 5,000 peaks into a visual heat map of the pathways driving the biology. To truly see the city, we need to visualize the connections. Individual metabolites do not act alone. They work together in a complex functional hierarchy. For instance, we use VANTED to map your experimental data directly onto established biochemical maps. This allows us to see exactly where the traffic bottlenecks in the cell are. Then we have Impala, which gives you the total system view by combining metabolite data with gene or protein expression. It's like looking at the traffic map and the city's power grid at the same time. Finally, we use correlation-based network analysis. We look for metabolites that always rise or fall together, even if they aren't in the same traditional pathway. This strong correlation suggests they are part of the same molecular neighborhood. This is the pinnacle of the omics pipeline, seeing how the city breathes, consumes energy, and responds to stress. Let's wrap up this strategic audit. You've just mastered the blueprint for navigating massive omics studies. We've learned that the pipeline begins with spectral processing to clean the raw harvest. We use the Schematsky scale to communicate certainty, and we use ORA and QEA to understand the workload of a biological system. Finally, we've seen how tools like VANTED and Impala turn isolated data points into a functional biological map. Remember this, data is just noise until you find the pathway it belongs to. You are now a pipeline architect. But there is one final question. How do we ensure we catch every important molecule in our net in the first place? Get ready. In our next session, Module 10-3, Harvesting Strategy, we are going to master DDA and DIA, the two fundamental ways we capture data at high speed. I'll see you at the harvest.